All right, so today we're going to talk about all of our matter vocabulary. So this will be the main words we need to know for our entire matter unit. I have them set up in each section like I did with our past waves unit, so that we can kind of organize it a little bit by 1.1, 1.2, and so on. All right, so we're going to start with section 1.1. So if we're going to have a unit on matter, then we definitely need to make sure we define what matter is. And so matter, well, is anything that has mass and takes up space. So this is pretty much everything you're interacting with in your world. You can think of it as stuff, okay? So it's all the stuff around you, or all the stuff around you is matter, and you're matter too. For example, air, plastic, and metal are all matter. Pretty much anything is matter. If it's a thing, it's matter. Okay? And so I have, this metal bar, that's absolutely matter. These plastic Lego blocks are absolutely matter. Anything that takes up space, which is pretty much anything you interact with, is matter. Even the air is matter. You may not think about it, but it's just not solid. A lot of people think only a solid can matter, and that's not true, and we'll talk about that a little bit later. We also need to talk a little bit about this word chemistry. Now you've heard of chemistry, and we don't go into a lot of detail. We just generally talk about the idea of chemistry. And so chemistry can be defined as the study of matter and how matter changes. For our purposes, that's what it's going to be. So that means the states of matter is a way we classify materials in chemistry. So we can classify different materials in 3 different categories, all right? And that's going to be a gas, a liquid, and a solid. You'll notice all these particles, we've talked about these in the past, these atoms, are situated a little bit differently in each one. In the gas, they're a lot more spread out. There's not much space between them. That's why the air, you don't think of as solid. You move right through it because there's all this space between these particles. And remember, these particles are microscopic. They're super, super small. We can't see them without specialized equipment. With a liquid, right, if you were to brush your hand through it, you can absolutely feel it, but you can typically move your hand through the liquid without too much difficulty. The solid can be a lot harder, so there's not much space between them, and that's why typically a solid, our hand won't move through very easily or really at all, and that all deals with how these things are set up, right? If you think about, water, steam, you can easily move your hand through that. If you think of water like in a pool, you can easily move through that, but ice, not so much. Building off of this idea is the word substance. And so, for our sake, we're going to call it a single kind of matter that is pure. And so sometimes we'll call it a pure substance. And our example could be table salt. It's just one thing. Like if it's truly a pure substance, one thing, it has just salt in it, and for our example here, okay? Or it could have, just water. Most of the time when you're drinking water, it's not just water. There's actually a lot of other minerals in there that can actually be good for us, and they're not harmful, but it's not technically pure water. So talking about this idea of states of matter, we also then will define that word solid a little more specifically. So it can be defined, our general definition has a definite shape and a definite volume. So it holds itself together, it stays that shape. And so because I wish I had a whole bunch of them, we could talk about a gold bar, and that's our image over here. And with just bar, it's going to stay that shape unless we do something to it. But if nothing hits it or we drop it or whatever it might be, it's going to stay just the way it is. It doesn't need, a container to hold its shape or anything like that. It just is what it is. A liquid, on the other hand, is a little bit different. So it has a definite volume, but no shape of its own. All right, so it'll take on the shape of its container, but it keeps that volume, but there's no real shape that it has. But if you have 100 milliliters of water, it stays 100 milliliters, whether it's in a puddle or in a glass. It's still 100 milliliters of it, it just has a different shape. So drinking water, and we're talking not frozen or in gas form, right? So drinking water could be our liquid. We also want to talk about this word fluid, and we've mentioned this a couple of times throughout the year. It can be defined in 2 different ways, whatever works best for you. A substance that flows, which kind of helps us, but sometimes you need a little more detail. So you can also think of it as freely moving particles, allowing them. Oh, we have an extra A in there. I don't need that here. Let's cross that off here. We don't need that. Allowing them to move from place to place. Okay, we talked about how a fluid can be a gas or a liquid. Okay, in this case, I used a kind of more of a gas. So a fog machine creates smoke/fog, which is a fluid. But water, what we just had before, that can absolutely be a fluid too. So with that, we can talk about the word gas, all right? So it has another definite shape, or nor. Ooh, I just have all sorts of typos, guys. I'm sorry. So that should be nor a definite volume. Here we go. So a gas is just, it'll spread out, it'll fill the entire area that it has, and it can definitely, its volume will change a little bit based off of that. And so that's what makes it a little bit different than our fluid. So dry ice will produce smoke, a gas, when at room temperature. So that's what this is kind of showing. And actually we kind of have this bubble shape here because there is this, it's essentially a bubble, there's this coating, it's actually holding it all together. You can look up a video of this and what will actually happen is this bubble eventually pop and the gas will almost just completely envelop this whole area. I mean, it'll just spread out all over. And it's really cool. So right now there's all this gas kind of held in this bubble, and eventually you'll see it kind of pop and it'll spread all over the place. So I just can't quite put that video in here for you guys to see. Alright, so we just talked about all the basics we need to know about matter, how we define what matter is, the different states it can be. So let's now take it a step further and move on to 1.2. Our next word is going to be melting, or to melt, and so it's a change in state from a solid to a liquid. This is not a new word for you. You know what I mean? You will regularly say, oh, that ice is melting. And that's absolutely true. And melting, so our example is an ice cube in above freezing temperatures. It will melt. You take the ice out of the freezer, you let it sit out, it'll eventually melt. So what determines if something melts? Well, we have to look at its melting point, the point at which something melts. So melting, that occurs at a specific temperature. So the melting point for ice is a temperature above 0 degrees Celsius. All right, so if it's above 0 degrees Celsius, or you may be more familiar with 32 degrees Fahrenheit, then that ice will melt. And so this ice cube will be bottom table, and eventually this will start to melt. You can see a little bit of water. It's kind of hard to see. This ice cube will begin to melt, just like in that previous picture as well. Our next word we're going to talk about is freezing. So it's the change of a state from a liquid to a solid. So we just had melting, which was solid to liquid. Now we're going from liquid to solid. So when water turns into ice. In this case we have our ice cube and we have water here. What's actually going to happen in this, we can't really see it go on. This ice cube gets put into this water. This water is actually really, really cold. And what happens when this ice enters it, it'll rapid freeze, it'll kind of flash freeze. And we'll watch this video in class so you guys can kind of see this happening, in which it just almost instantly freezes. It's really, really cool to watch. Next, we're going to talk about vaporizing. So vaporizing is the change in state from a liquid to a gas. So now we're talking about if we have, say, water, and we're going into water vapor, or vaporizing. So when you throw boiling water into freezing air, it will vaporize, turning into a gas. So if you've never done this before, you have to wait now that our winter's over. But next winter, boil some water with parent supervision, because boiling water can be dangerous if you spill it. And especially on a really cold day, go outside and toss the water into the air. What'll happen, and you don't have to do it just like this. This is really cool, where they threw kind of over themselves and creates this cool image. But if you just toss it straight up or out and away, it'll actually never get to the ground because it'll turn into a gas, which will actually now kind of float away, which is really, really cool. Evaporation, when vaporization takes place only on the surface of the liquid. So a vaporization, evaporation is when it's only really occurring on the top of the surface. So a puddle of water on a road will go through evaporation. right? So you'll see just kind of the top part go away, and as that part goes away, then the new surfaces change, and it'll slowly work its way down. It's not happening from all over the place. So vaporization and evaporation are a little bit different. Where vaporization is the general term for it, evaporation is essentially a specific version of vaporization. So vaporization is a little more general. And so you've probably seen a lot of puddles like this on the road, especially after some rain or something like that. And then you get a really sunny day, that puddle eventually gets smaller and smaller and smaller throughout the day because it's evaporating, and the water is turning to gas, which is vaporization. Next, we can look at boiling. So boiling is when vaporization takes place both below and at the surface. So we get some gas forming on the top of the liquid, and you'll see that, right? You see the bubbles of steam coming off. But it also happens at the bottom, because remember, the bottom of the stove is really hot, right? It's got a really high temperature, and that heat is then being transferred, right? The heat's that transfer of energy, so heat's going towards or into the water, which heats it. Now, if you ever look at a boiling pot of water, if you've ever done this, have a look. You'll see bubbles start to form at the bottom. Usually we'll call this simmering. It's right before it starts to really boil, like it is in this image. You'll see these bubbles from the bottom rise to the top. Those bubbles are formed by vaporization. So there's these little pockets of, well, water vapor in the water. And it rises because it's lighter than the water, and then it eventually gets to the surface, and it'll open up, and you get the steam. So it's happening at both locations, at the top and at the bottom, and the bubble slowly goes up, and then it escapes out. Boiling point, so just like melting point was the point at which a solid turns to a liquid, boiling point is when we have a liquid boiling, so that temperature in which it'll boil, and then that'll have from a liquid to a gas. So the boiling point for water is 100 degrees Celsius. Okay? And so we can add a mark. If something's at 100 degrees Celsius, it'll start to boil, changing from a liquid to a gas. Okay, our next word is going to be condensation. So it's the change in state from a gas to a liquid. So we just talked about liquid to gas, now we're going gas to liquid. And so the water that forms on the outside of your glass of water, or any beverage you have. A lot of people go, oh, my glass is sweating. It's not true, and your glass isn't leaking either. It's not like a little bit of water is getting through the glass and getting to the outside. It's actually the water that's in the air around you. There's a little bit of water in the air around you. Not a lot, but a little bit. Sometimes you'll notice it more if it's a really humid day where the air actually feels wet, or sometimes paper can feel damp. And if it's a really warm day and you have a really icy cold glass of water or lemonade or whatever it might be, and you let it sit for a little bit, then you go to pick it up, suddenly it's all wet. And you're like, well, what the heck? What's going on? It's cold enough in the glass that it causes this change of gas to change to a liquid, because gas exists at a much hotter temperature, and then liquid will be at a cooler temperature, and so this really cold drink that we have with all this ice is so much colder than the temperature on the outside that little water droplets get attached to yours, because the water that's right next to it that touches the glass changes from a gas to a liquid. All right, and now we're on to section 1.3. So we just talked about a whole bunch of what matter is, the different states it can go through, what do you call those changes. Now let's talk about how we can describe these things more specifically. So if we're looking at that, we have physical properties of matter. A physical property is going to be a characteristic that can be observed without changing it into another substance. So we strictly just look at what is it that makes it what it is right now. It's a physical characteristic. So for an example is an apple has physical properties such as it is spherical, red, has a smooth surface, etc. Basically, we can be very descriptive. The things that we can describe about its physical appearance. In addition to a physical property, we can talk about a chemical property. A chemical property is a characteristic of a substance that describes its ability to change into different substances. So chemical properties are when they change to something completely different. So iron will turn into rust as it is exposed to the air and water. So we can see this bike has been sitting out and it's made of iron or some form of metal with iron in it. And you can see some of this rust starting to form. We realize how more and more of that rust will form. That's changing it. Once the iron changes into rust, and we talk about what rust actually is, it's change. It's a chemical change. You can't reverse it, right? There's rust cleaner, but that just removes the rust, doesn't convert it back. And so that's why it'd be a chemical property, and we'll talk about how we define that with the changes in a moment here. Okay, section 1.4, last section. We can do it. A physical change is going to be when a physical change when the form or appearance of a substance is changed, but it still remains the same substance, which means it's reversible. So our example is the changing of water to ice. So we have water, goes through a change, we get ice. Ice can melt, we have water again. It's the same thing, just really physical change is just changing the state that it's in. Liquid, solid, gas, any of those things. Or maybe we're changing the shape, right? So maybe we have a metal bar and we bend it into kind of a horseshoe shape. Had a physical change, it's bent now, but it's still the same thing. It's still, iron bar. Okay, law of conservation of mass. We talked about the law of conservation of energy earlier in the year. It's really the same thing, except instead of energy, we're looking at mass or matter. And so matter cannot be created or destroyed, is the simple definition. The idea being, how much stuff we have is how much stuff we have. We don't make more, we don't destroy it, we just really convert it to different forms, and it can constantly be converted to all these different things. So the amount of matter before a reaction is equal to the amount after. So if we have a bonfire, we have our wood, and then there's fires burning, and then there's some oxygen that we need, right? And then there's carbon dioxide and water vapor, all these different things going on. And when we let the fire burn, we get this ash, and it looks like we have a whole bunch less stuff, right? You think that pile, the fire burns down, and right, if you thought of all the wood you put into a bonfire, it's not like you have this giant mountain the same size, it's smaller. So what the heck's going on? We just said our matter cannot be created or destroyed, but it looks like we just destroyed a whole bunch of things. We did it, and we'll look at this in class. The reason I have this question marks here is there's a whole bunch of, right, you feel that heat and there's all that smoke and all those things. Well, there's a change happening in which some of the matter is actually being turned into a gas and escaping and going elsewhere. It still exists. It's just not there anymore. And that's where I think people get tripped up. They think, oh, well, this is less than it was before, so it must have destroyed matter. No, it just went away. Like, it still exists. It just went to a different spot. We've talked about energy a couple of times. So, right, energy is the ability to do work or cause change. A battery stores energy allowing work to be done, right? We can store that energy in a battery. We can plug that battery into a tool and work can be done, right? Think maybe you take a battery, you put it into a battery-powered drill, and you actually, you put up a new fixture or you drill a hole in a wall, right? You do some work. And that required energy. Without the battery, nothing would happen. The drill wouldn't work, right? We've also talked about temperature. So temperature is the measure of the average energy of random motion of particles of matter. Remember, with temperature, it doesn't matter how much we have. Temperature is temperature. If we have a small piece of it, it could be at 100 degrees Celsius. If we have a whole bunch of it and still at 100 degrees Celsius, it has nothing to do with the amount of it we have. It's strictly the measure of the average energy produced by each little particle. So as the movement of particles increase, so does the temperature. So low temperature, we have these, and they're moving around. If we add heat, add heat, temperature, and heat then transfers, we get a really high temperature. You notice that these look like they're moving around a lot faster. And we've looked at images like this a couple of times throughout the year, so hopefully we're starting to get that idea. The one thing that typically always gets confused with as temperature is thermal energy. Thermal energy is the total kinetic and potential energy of all the particles of an object. That's the key piece in that definition. Okay? All the particles. Okay, that's a really important piece to make sure we're getting. And the idea that if we have a really small object and a really big object and they're the same temperature, the bigger object's going to have more thermal energy because there's more things contributing energy. When particles get hotter, they move faster. When they are colder, they move slower. So it's similar to that temperature piece. When they're dealing with the movement of particles, thermal energy just counts the fact how many of them there are. So in this case, we have a high temperature. In this case, we have a low temperature. And since they're the same size, in this case, they would also have a greater thermal energy. I also threw in here a little bit of that heat flow, right? Hot to cold, reinforce that until eventually they'll be balanced in these two blocks and they'll have equal temperatures. Our next word, compression or compress. And you have a general idea of what, if you compress something, you're pushing it together. And so in this case, our definition for our purpose is just pressed tightly or pressed together tightly. So if we have a spring being pressed down on, so we have this spring and we have something, we push it down, we get compression going on, and that's why that's much more tightly packed. It's compressed. We also want to talk about something called thermal expansion, and we briefly talked about this throughout the year. It's the idea that as things get warmer, they tend to expand. And so it's the expanding of substances as their temperature goes up. So water taking up more space as it heats up. So in this case, we have water at 70 degrees. Now in this scenario, they're going to be having it at, they don't have it marked, which is kind of unfortunate for this image, but I'm going to assume it's in Fahrenheit because 70 degrees Fahrenheit is room temperature, so that's just water. Okay, so let's actually go ahead and add in that unit here, and you make sure you do the same. So we got Fahrenheit at 140 degrees Fahrenheit and 180 degrees Fahrenheit. And we can tell that we're adding more heat. You can see the flames underneath. And as this temperature goes up, you notice the water level rises. And we've kept this sealed the whole time. So we haven't actually added more water. It's just actually expanded a little bit and risen, and pressure would increase. And eventually, if we did this and you had enough, it would expand to the point where it could overflow. Right? I don't know if you've ever had this happen at home, if maybe your parents have been cooking and if they're boiling water and they kind of forget about it, they'll go, oh shoot, it boiled over. That's because it expanded. It boiled over the container they had it in because it needed more space and there wasn't any space for it, so it boiled over onto the stovetop. The last word we need to talk about is diffusion. So diffusion is the random movement of particles from a high concentration to a low concentration. So food coloring gradually mixing itself over time. So if we pretend that we have this glass of water and we add like a drop or so of food coloring, so let's say it's red food coloring, these are all the particles that make up it. If we let it sit, it will eventually mix the whole way through. Now we don't touch it. We just let it naturally diffuse. We can speed this process up by, say, stirring, but if we were just to put a drop in there and didn't do anything, it eventually would mix. It would just take a little bit longer, but it eventually would. And that's diffusion, in which things like to be balanced in nature. And so in this case, it's not balanced, right? So all these little particles, they like to have their space. And right now they don't have their space, so they want to spread out. So eventually they'll spread out to be about as equal as possible as far as the distance between all of them. It's the same reason why typically when you come into the classroom, especially maybe the first day of school, you come in, you have a seat, you don't all suddenly like sit all in one corner, right? As students, you don't try to pack it as tightly together as possible. You generally all spread out in the room a fairly even amount. You do this naturally as well. So that's it. That's all of our vocabulary for our matter unit. If you have questions, please let me know in class. Otherwise, thanks for watching.